In the last video in this series, we're going to take a look at applications of the partial derivative. In fact, that's what we're going to be looking at for the remainder of this section. And we're going to start by being able to verify solutions to partial differential equations. So for those of you that have to take partial differentials, at some point, you're probably going to be, this would be the first day of class, first type of problem you look at, is verifying that a proposed solution does indeed satisfy a differential. And so let's take a look and determine whether or not a few different proposed solutions are going to satisfy a differential. So we have this equation, Laplace's equation actually, and we're proposing that a possible solution to Laplace's equation is e to the x sine y. All right, so here's what we're going to do. We're going to start by finding the second partial of u with respect to x. Okay, so let's start by finding the first partial. So partial of u with respect to x is going to be really easy. E to the x sine y. Can't get that one wrong. All right. Second partial. So second partial of u with respect to x is going to be e to the x sine y. In fact, any nth partial is going to be e to the x sine y. Now, let's find the partial of u with respect to y. That's going to be pretty easy. That's just going to be e to the x cos y. And then finally, the second derivative with respect to y, partial of u, second partial of u with respect to y is going to be equal to negative e to the x sine y. And so now we just throw those into Laplace's equation, which is second partial of u with respect to x plus second partial of u with respect to y is e to the x sine x minus e to the x sine x, and clearly that equals 0. And hence we verified that this solution, e to the x sine y, satisfies the differential. A second example. So we have L partial p partial L plus k partial p partial k is equal to alpha plus beta plus p. And p is said to be equal to b L alpha k beta. All right, this is actually something called the Cobb-Douglas function. It's used to model businesses with productivity as well as overhead costs. And what we're doing is we're trying to determine whether or not this solution does indeed satisfy it. All right, so let's see what happens. We're going to take the partial of p with respect to L. All right, so we're just taking this equation, and the derivative with respect to L is actually pretty easy. We're still going to keep the b. We are going to have times alpha, L alpha minus 1. All right, so we're just basically using the general power rule on L, and k beta stays exactly what it is. Now the partial of p with respect now to k. All right, so all I'm doing is I'm just finding these partials. We're going to do the exact same thing. So we're going to get b L alpha, and then the derivative of k beta, or k to the beta, is going to be beta k beta minus 1. And now we're just going to throw it back into this partial differential. So L partial p partial L plus p, or I'm sorry, k partial p partial k is going to be equal to, now we're going to substitute, we're going to say L times this b alpha L alpha minus 1 k beta plus k times the answer that we just got for partial of p with respect to k. So that's going to be bl to the alpha times beta k beta minus 1. All right, so now what you'll notice is that we can go ahead and we can kind of integrate that L into the factor. All right, so this is like an L to the first, and so what that would do is that would actually cancel out the negative 1, and then we have a K to the first power, which would cancel out this beta, or the minus 1 on the beta. All right, so what we would end up with is, just by going through and distributing, is going to be B alpha, L alpha, K beta, plus B L alpha, beta, K beta. All right, that's just algebra there. And I want you to notice also that there's a lot of common factors that are going on here. So notice that what's common between those, L alpha, K beta, B. And so we can factor those out. And if we do that, we're going to get B L alpha, K beta. And what's going to be left over? Alpha plus beta. And then finally, what is BL alpha K beta? BL alpha K beta is P. So we can rewrite that as, this whole thing is just P alpha plus beta. And we're hoping that that's the solution that we're looking for. And if you notice, we have right here alpha plus beta times P. And so that verifies that indeed this is the solution to the differential. All right, one last example, going back to Laplace's partials. So we have second partial of u with respect to x, second partial of u with respect to y is equal to 0, and this time we have the natural logarithmic function. All right, so this one's a little bit more painful, and I'll illustrate why. Okay. But for right now, let's just go ahead and see if we can find those second partials. All right, so now the first partial is pretty easy. All right, so let's just find partial of u with respect to x. And if we do that, that's going to be equal to 1 over x squared plus y squared times the derivative of the interior function, which is 2x. All right, now there's two ways to write this. One of which is we could just write it as 2x over x squared plus y squared. Another way to write it would be 2x x squared plus y squared to the minus 1. And I'm going to write it that way because when we find the second partial, we're going to need to use the product rule, which sounds bad, but it's better than using the quotient rule. All right, so if we took the derivative in this first form right here, we'd have to use a quotient rule. And I always try to avoid using the quotient rule whenever possible, just because then the denominator just gets really ugly. So second partial, second partial of u with respect to x, we're going to have our product rule. Derivative of 2x is 2, and we still have that x squared plus y squared to the minus 1. And then we're going to take the derivative, we're going to keep the 2x as is. We're going to move the negative in front, so it's going to be minus 2x. And then we have x squared plus y squared to the minus 2. And then we have a derivative of the interior function with respect to x, which is another 2x. All right, so all of that said, we end up with 2 over x squared plus y squared minus 4x squared over x squared plus y squared squared. All right. Now, we usually don't have to do this, but in this case we probably should do it. Let's get a common denominator. Right? And if we do get a common denominator for this, We're just going to multiply the first equation by x squared y squared on the top and bottom, since the LCD is going to be x squared plus y squared squared. So we're going to get 2x squared plus y squared minus 4x squared over x squared plus y squared square. And then mercifully, we end up with a simplistic quote-unquote answer. We have 2 minus 4, so we get minus 2x squared plus 2y squared all over x squared plus y squared squared. All right, so now let's hold on to this, because that's our second partial, fxx. Of course, we still have to find fyy. All right, so we're getting there. All right, so to be able to find that, just going to give ourselves some room here. All right, so now we're going to find partial of u with respect to y. And that's pretty easy for the first one. All right, remember it's 1 over x squared plus y squared because of the ln. And then we're going to multiply that by the derivative of x squared plus y squared with respect to y, which is 2y. Let's rewrite that similar to how we did it before. So 2y x squared plus y squared to the minus 1. And now we're set up to use the product rule, and I think you know where this is going. We have the second partial of u with respect to y, and derivative of 2y is just going to be 2. So we have 2, and then we have x squared plus y squared to the minus 1. We're going to drop down that negative 1, so minus 2y x squared plus y squared to the minus 2, and then the derivative of the interior x squared plus y squared with respect to y is going to be 2y. We can rewrite that as 2 over x squared plus y squared minus 4y squared divided by x squared plus y squared squared. Just like before, we're going to get a common denominator, and we're going to rewrite this as 2 quantity x squared plus y squared minus 4y squared all over x squared plus y squared squared. And now we can simplify this. Notice we have 2y squareds, negative 4y squareds. So this is going to simplify into 2x squared minus 2y squared all over x squared plus y squared squared. And so that's our fyy. And Laplace's equation says that fxx plus fyy is going to be equal to 0. Well, remember, initially we got for fxx, okay, which is the same thing, by the way, as second partial of u with respect to x squared. So just making sure that we understand that these two things mean the same. I just wrote it as fxx because it's a little bit quicker. Notice we have negative 2x squared plus 2y squared all over x squared plus y squared squared. And then we're just going to drop down the solution that we just got. So 2x squared minus 2y squared over x squared plus y squared squared. Notice the denominators are exactly the same. We combine like terms, and 2x squared cancels with 2x squared, 2y squared cancels with 2y squared. We end up with 0 over x squared plus y squared squared, otherwise known as 0. And that's a good thing, because all the way back up here, remember we said that we wanted Laplace's equation to be equal to 0 after we found those partials. All right, so hopefully this is a good introduction for you all to be able to understand how to utilize, or first of all, how to find partial derivatives, and then secondly, how to utilize those partial derivatives to be able to solve or to verify these partial differential equations. The next series of videos, we're going to be taking a look at further applications of our partial derivatives.